Hello and welcome to this video. In this video we are going to be covering the Edexcel A Level Maths Paper 1 from the June 2019 series. This is the first out of the 3 papers and this covers the pure mathematics element of the course. In question number 1 we are given a function f of x and this equals 3x cubed plus 2ax squared minus 4x plus 5a, where a is a constant. Given that x plus 3 is a factor of f of x, find the value of the constant a. Now this question is all about a topic that you would tend to cover in year 12 called the factor theorem. And what the factor theorem states is that if you've got a factor of f of x, say x plus 3, f of minus 3 is going to equal 0. So according to this factor theorem, if we take f and we substitute minus 3 into each and every x here, you'll find that it equals 0. So completing this, or applying this theorem, we are going to be finding the value of this constant. So 3 times minus 3 cubed, since the x is cubed here, plus 2 times a, which is our unknown constant that we're trying to be working out, times by minus 3 squared, minus 4 times minus 3 plus 5a equals 0. So what I'm going to be doing here is I'm going to be multiplying this out. So what you get is 3 multiplied by minus 27, minus 3 cubed is minus 27, plus 2a, minus 3 squared is 9, minus 4 times minus 3, positive 12, plus 5a equals 0. Now I'm going to multiply this out and rearrange it. And what we get is 23a equals 69. Divide both sides by 23. And we're left with a equaling 3. Figure 1 shows a plot of part of the curve with equation y equals cos x. So what we're getting here, we're getting part of the cosine graph where x is measured in radians. And this is going to be a key part of this question, so I'm just going to underline that. Diagram 1 on the opposite page, so on the page here is it's a copy of figure 1. So what we're going to be doing is we're going to be using diagram 1 to show why the equation cos x minus 2x minus a half equals 0 has only one real root, giving us reason for our answer. Now, what we need to do with this is we need to sort of really make use of what we're given. We're given the fact that we need to use this diagram here, this diagram that's representing the cosine curve or part of the cosine curve. So our first step should be to sort of do something with this here. So what we're going to be doing here is that we're going to be sort of rearranging this so we have almost a simultaneous equation taking place. So what we have is we've got cos x, and I'm going to take this to the other side and taking that to the other side equals 2x plus a half. So in terms of this equation only having one real root, that will be the case if these two curves have only one intersection. So let's take ourselves back to our diagram and look at ways in which we can apply this. So we've got our cosine graph. That makes the sort of left-hand side of this simultaneous equation complete. And what we're going to be doing is we're going to be linking it to the right-hand side of the equation, which is this linear line. And this linear line has a y-intercept of a half. And we should know now that the highest point, or the range, of the cosine curve goes from 1 to minus 1. So with this being a y-intercept of a half, we're going to be looking at it sort of intercepting at this point here. And what I'm going to be doing is I'm going to be plotting that, plotting the line in. And what we'll find is that if we plot it in with a gradient of approximately 2, this question doesn't require you to be exact, and put it with a y-intercept of a half, okay, and making it very clear that this is intersecting the y-axis at a half, what you'll find is that there is only one point of intersection, and this here will give you the value of the real root. So what we're going to be doing is we're going to we've used the diagram to help us with our answer, and we're just going to be sort of aiding that, providing this reason for your answer, making sure to read the question properly and following all set instructions, and stating that there is only one point of intersection on the graph. Okay, so for part B, we're going to be sort of continuing this equation further. And I believe that what we're going to be doing is we're going to be using small angle approximations. Okay, so we need to remember our three small angle approximations for each trigonometric function. So sine theta approximates to theta. Tan theta also approximates to theta. And cos theta is a bit of a weird and quirky one, because what cos theta approximates to, when theta is measured in radians, okay, so that's why I underlined it there, and is small, cos theta approximates to 1 minus theta squared over 2. And what we're going to be using is we're going to be using this one here. However, sort of the theta and x are indeed interchangeable. So for B, what we're going to be doing is we're going to be getting sort of this small angle approximation, putting it into our sort of equation there. So we've got 1 minus theta squared, or I should probably go back and turn that into an x squared, over 2 minus 2x minus a half equals 0. And almost what we have here is that we've got a quadratic equation. So what I'm going to be doing here is I'm going to be sort of collecting like terms. So we've got 1 minus a half, which is a half. So we should have minus x squared over 2 minus 2x minus a half, plus a half, sorry. And that equals 0. And what I'm going to be doing is I'm just going to be moving all this to the other side. So we've got this x squared term as a positive term. Okay, and just to get rid of these fractions here, I'm going to be timesing everything by 2. So we have x squared plus 4x minus 1 equals 0. And now what we're going to be doing is we're going to be solving this quadratic. And what we should find is that the one real root of this equation, so we're going to be taking the real root here. Okay, so you put this into the calculator, because remember you have full access to the calculator for every exam for your A-level maths course. And what you'll find is that the one real root is minus 2 plus root 5. And that is your answer. In question number 3, we have got that y equals 5x squared plus 10x over x plus 1 squared. So we've got an x function on the numerator of this fraction and an x function on the denominator of this fraction. And for part A, we are asked to find the derivative of this. So what we know is that where we've got an x function on the numerator and an x function on the denominator, we'll have to apply the quotient rule of differentiation. And for those of you that may have sort of forgotten this, the quotient rule is that wherever you've got, or wherever you're trying to work out the derivative of a particular function, we've got an x function on the numerator, and we'll call that u, and an x function on the denominator, which we'll call v. The derivative is going to equal v, so the denominator, times by the derivative of the numerator, which is going to be du over dx, and from that we're going to subtract the numerator multiplied by the derivative of the denominator, and we're going to be dividing that by v squared, so the denominator squared. So what we're going to be doing is we're going to be sort of applying that within what we've got here. So our numerator is 5x squared plus 10x, and our denominator is x plus 1 squared. So our denominator, v, times by the derivative of the numerator, so we've got 10x plus 10, basic differentiation there, And from that, we're going to subtract the denominator, or the numerator, sorry, which is our u, times by the derivative of the denominator, which is x plus 1 squared. And for this, what we're going to be having to use is the chain rule. So the derivative of x plus 1 squared, we take this there, and then we multiply that, our answer, by the derivative of what's inside of the bracket, which is 1. So we're going to be getting 1 times 2 times x plus 1, which is just 2 times x plus 1. Put the 2 there, and the x plus 1 there. And that's going to be over, okay, v squared. And our v squared is going to be x plus 1 squared, which is going to be x plus 1 to the power of 4. Now, wherever we've got questions where we've got quite a sort of messy fraction here, and we've got quite a neat looking end that we want to this particular fraction, it's all about sort of trying to pick out particular details, trying to pick out particular patterns amongst the chaos, amongst the mess, that can result in something a little bit more peaceful, a little bit more simple. And what I'm sort of gathering here, just looking at what we have here, is that we've got x plus 1 in each of the three terms. So in this term, we've got an x plus 1. In that term, we've got an x plus 1. And obviously in the denominator, we've got 4 of them. So what I'm going to be doing is I'm going to proceed by taking out x plus 1 from both the numerator and the denominator. So I'm going to be putting x plus 1 outside, and I'm going to be timesing that by x plus 1, timesing that by 10x plus 10, and that is obviously subtracted from 2 times 5x squared plus 10x, where we've taken this out. And obviously going to be applying the same to the denominator. And we're going to be cancelling this out. So now what we're left is something a little bit more tidier. And I'm going to proceed by multiplying these sort of simple brackets and expressions out. So 10x squared plus 10x plus 10x plus 20x and plus 10. I'm going to subtract that from that we're going to subtract 10x squared and 20x. And that's all over x plus 1 cubed. And obviously now, okay, because we pulled out the right expression of x, things have fallen into place quite well. We're able to cancel out these x squared terms. We're able to cancel out these, obviously, 20x terms here. And what we're left is 10 over x plus 1 cubed. And what we find is that this fits the exact form that we're asked to sort of put this in. So sort of where a equals 10. Part B, we're asked to deduce the range of values for x for which dy over dx is less than 0. So we want, for part B, 10 over x plus 1 cubed to be less than 0. In other words, we want this expression to be negative. In order for that to be a case, since we've got a cube term here, we need whatever is inside of this bracket to be negative. And for this to be negative, you'll need x to be less than minus 1. If it's anything greater than minus 1, or indeed if it is minus 1, you're going to be ending up with 0 or something greater. Therefore, for it to be strictly less than 0, this term within the bracket is going to be negative. It's going to have to be negative. And for that to happen, x has to be strictly, so we're not being putting sort of, we're not going to be inclusive here with this inequality. It has to be strictly less than minus 1. And that's the answer for that question. For question number 4, in part A, we are asked to find the first three terms in ascending powers of x of the binomial expansion of 1 over root 4 minus x. And what we're asked to do is give each coefficient in its simplest form. And really the sort of main and primary step to solving this is to ultimately describe 1 over root 4 minus x in index format. And that really is how we get to expand binomially sort of expressions like 4 minus x. And what we can see here is that what we've got is we've got an equation where, or an expression that's being put to the power of a particular negative fractional indice that has a non-one term here. And really what we need to do in that case is manipulate this expression in such a way where this term here becomes a 1. And to do that, what we're going to be doing is we're going to be pulling this 4 out. And in the end, what we get is this here. Okay, because remember, in order to sort of binomially expand a particular expression that has a negative or fractional indices, or like this, a combination of the two, you really must have it in the form of 1 plus ax. 1 plus or minus ax, because indeed that a can be negative. And in cases where you may have a non-one term here, what you really have to do is pull that out. And now that we've pulled that out, what we really need to do now is apply this indice to this term and apply it to this term as well. And what we get is 4 to the power of minus a half, and that's going to be multiplied by 1 minus a quarter x to the power of minus a half. 4 to the minus a half is 1 over root 4, which is quite obviously a half, and that's going to be multiplied by 1 minus a quarter x to the power of minus a half. And really what I want to be sort of using here is the binomial expansion formula for negative indices, fractional indices, or negative fractional indices like this. And what it really does comprise of is when you're sort of expanding sort of a term like this, to a negative fractional indice, the sort of expansion takes the following formula. So you have 1, you add a, okay, and what you do is you add a or a times by the sort of indice that you have there. So you have a nx, okay, and then what you do to that then is you add n minus 1 over 2 factorial, which is 2, and that's multiplied by a squared x squared. Okay, and since what we're looking for here are the first three terms, first three obviously non-zero terms in ascending powers of x, that really is as far as we need to go in terms of this formula. But obviously it is continuous to an infinite degree. So really what I want to be doing here now is inputting what we have here into this formula that we've got here for our negative or fractional indices. So we're going to be still having a half, but this time it's going to be multiplied by 1, okay, plus minus a half, okay, and that's our n, multiplied by ax, which is going to be minus a quarter x. And that's going to be added to n, which is minus a half, multiplied by n minus 1, which is going to be minus 3 over 2. And that's going to be multiplied by a squared, so minus a quarter squared, multiplied by x squared over 2. Okay, 2 factorial, in other words, 2. So I'm going to sort of simplify this and multiply it out. And what we're going to be getting as a whole is a half. Okay, that's obviously when you've simplified this, so you've multiplied all these numbers out and you've times each of the 3 terms by a half. What you'll get is this. You'll get a half plus x over 16 plus 3x squared over 256. Okay, and that there is the answer to part A. Part B now. Okay, so what part B is asking is to state, giving a reason which of the 3 values of x should not be used. And really what they're doing in part B is to use this approximation in order to find, or using this expansion in order to find an approximation for root 2. Possible values of x that they have used are x equals minus 14. Now, just sort of observing that firsthand, that's instantly wrong, and we shall go on to sort of explain and describe why. X equals 2 and x equals minus a half. So what they're going to end with is these sorts of expressions here. For this, they can then times it by 6 in order to get root 2. For this, they can times it by 2. And for this, they can times it by 3 at the end. And really, sort of, we're trying to find which of these, so for part B, I, we're trying to find which of these values of x should not be used. In other words, what is invalid. Now, when you're expanding binomially an expression like this that to a negative or fractional indice, there really is one rule that really applies to substitutions and the range or the domain of these substitutions. And it's this idea that the modulus of a of x is going to be less than 1. Okay? And in this case, our ax is going to be x over 4. Okay, ignoring the minus sign, because what we have here is a modulus around the expression, and this has to be less than 1. Taking this 4 to the other side, x, in other words, has to be less than 4. The modulus of x has to be less than 4. Now this here is obviously greater, it's outside of that range. So this here instantly can't be used. And the reasoning we're going to give for that is quite simple. So we've chosen that x equals minus 14 can't be used, and that's because x has to be less than 4, and minus 14 is greater than 4, therefore invalid. For part B, I, what we're going to be doing here is we're going to be giving a reason which of the 3 values of x will lead to the most accurate approximation to root 2. And now this is a bit of a sort of esoteric, should we say, response, an esoteric, sort of very technical style of question. But what it really involves is this idea that a of x itself has to be sort of as close as possible to 0 in order to be able to get the most accurate approximation. Okay, and given our remaining values, we've got x equals 2, okay, and x equals minus a half. Let's find which leads to the closest value. So x equals 2, so we're going to be having minus a quarter times by 2, and we end up with minus a half. And x equals, and I believe it was minus a half. We end up with minus a quarter times by minus a half, and what we get is an eighth. And obviously, an eighth is closer to 0. Then we can sort of reason this by saying x equals minus a half is our chosen most sort of close approximation to root 2, because it is fundamentally closest to 0, and it all really is described by the way in which these sorts of binomial expansions converge. And really, with these sorts of negative fractional indices, they typically do tend to converge as the value of these sorts of denominators get greater and the value of these sort of fractions in the numerator gets smaller. And that there is the answer to question number 4.
For question number 5, we are given a function f of x, which is equal to 2x squared plus 4x plus 9. And for part A, what we're asked to do is put it in the form a, x plus b squared plus c, where a, b and c are integers to be found. So in essence, what we're asked to do here is to complete the square. And because the function that we've got here has a coefficient in front of the x squared term, what we're going to be expected to do here is factor that 2 out of the first 2 terms of this function. So what we're going to be getting is x squared plus 2x, and then on the end we just add 9. And now what we've got here is we've got a function, or we've got an expression here, x squared plus 2x, that we're quite simply able to sort of complete the square of, sort of individually and separately. And to do that, what we're going to be doing is we're going to be getting the x term, and we're going to be halving the coefficient of this x term here, which is 1, squaring that, subtracting, and this is a shortcut method here, subtracting the square of this term here, and we're going to be adding 9. And now what I'm going to be doing is I'm going to be multiplying this bracket out. So 2 times x plus 1 squared is 2x times x plus 1 squared, times 2 by minus 1, minus 2, plus 9, and what we get is 2x plus 1 squared minus 2 plus 9 plus 7. And that is in the form a times x plus b squared plus c, where a is 2, b is 1, and c is 7. For part B, what we're asked to do is sketch the curve with equation y equals f of x, showing any points of intersection with the coordinate axis and the coordinates of any turning point. Now, before we get stuck into this, what I want to sort of pick up are a few key points. We've got our function here, and this function is a quadratic. Okay, there's an x squared term, and that's the highest, indice that we can see here. It's the highest sort of power of x that we can see in the expression. And what that really tells us, combined with the fact that what we've got is a positive coefficient, is that we're really going to be getting a sort of U-shaped parabola. If this coefficient here was negative, what we'd get is an N-shaped parabola. But what we should be getting is something that looks a little bit like this. And now, in terms of the points of intersection with the coordinate axes and the coordinates of any turning point, well, quite simply, what we've done here is that we've sort of completed the square here, which has quite sort of simply lent itself to us being able to work out the turning point. So what we do here is, if we've completed the square, to work out the x coordinate of the turning point, we negate whatever term is here. So we negate positive 1 to get minus 1. And that gives us the x coordinate. And the y coordinate is whatever number is outside of the bracket, so that's going to be 7. And that there tells us the turning point. Now, in terms of the intercept, what we really need to understand is the fact that this turning point is above the x-axis. That shows that there's going to be no real roots. There's going to be no points at which the whole graph intersects the x-axis, and that means that we'll only ever intersect the y-axis. Now, to find out the point of this y-intercept, we're going to have to just sort of substitute 0 into here. So 2 times 0 squared plus 4 times 0 plus 9 is 9, and that tells us the y-intercept of the graph. So this there is the interception. Okay, so these are our 2 key sort of points that we're going to be taking forward with us when we construct the graph. So what I've got here is a set of axes, okay, and immediately what I want to be doing is I want to be just getting the turning point right. So what here, we've got minus 1 here, I'll call that minus 1. And we've got 7 here. And remember, guys, the question itself tells us to sketch the curve. So it's not a plot question, and you don't really need to be doing point by point. And at the same time, you don't really need to be making sure that everything is exact in terms of incrementations on the axes and whatnot. So what we've got here is the coordinate minus 1, 7, which is our turning point. And if we remember correctly, our y-intercept is going to be 0, 9. So if we just draw 9 up there, and now if I was to sketch this parabola, what we'll find is that we've got a sketch here of y equals f of x with this turning point and with this y-intercept. These here are the 2 key points in order for you to score all marks on this question. For part C, part I, we're asked to fully describe the transformation that maps the curve with equation y equals fx onto the curve with equation y equals gx. Now, in terms of these transformations, what you really want to be looking for are a set of patterns, okay? And what we can see here is a sense of commonality between f of x and g of x, where we've got a 2x squared term plus 4x plus 9. Here we've got a 2x minus 2 squared term plus 4x minus 3. I guess the most sort of simple assumption that someone would make is that g of x is f with x minus 2 substituted wherever you see an x on the f of x. However, if we see, that doesn't really apply to the 4x term here, okay? And also, we're seeing the constant here, where we've got 9 here and a minus 3 here, is different. So what we really need to be doing is we need to be manipulating the function that we see here as g of x in such a way where we're establishing that commonality between the two, okay? So what we're going to be doing is I'm going to be sort of trying to substitute x minus 2 here, expanding it out and see how we can manipulate it so we can get the same result. So we've got 4x minus 2, we expand this out, we'll get 4x minus 8. In order to get that minus 3 on the side from minus 8, we just need to add 5. So g of x is also equal to 2x minus 2 squared plus 4x minus 2, and just adding a 5 on the end. So when it comes to sort of describing the transformation between g of x and f of x, g of x is indeed f of x minus 2, but we can see that there is a different constant. It's gone from 9 down to 5, so it's clear that minus 4, or that 4 has been deducted from the function between f of x and g of x. And now, when we can remember our rules from transformations, we can realise that whenever we've got something within the bracket next to the x, the number here impacts the x. However, when it's in the bracket, it does the opposite to what you'd expect it to do. Instead of going 2 to the left, it would go 2 to the right. So you're going to be seeing a shift of 2 to the right. Equally with this here, this is outside of the bracket. It impacts the y part of the graph, and what it does is that it brings the whole graph 4 units downwards, okay, because it does what you expect it to do because it's not in the brackets. So what I'm going to be doing here is I'm going to be, for part CI, I'm going to be describing this transformation. So we've got y equals f of x here. I'm going to be describing such a transformation where we're taking it 2 across and 4 downwards. So we'd get something, g of x would look something on this part of the graph here. And such a transformation, and remember we have to describe fully the transformation that takes place. And such a transformation where you're moving it 2 along and 4 down is a translation. And to describe these translations, what we use are vectors. And since it's going 2 along, we're going to have positive 2 on the x part of the vector. And since it's going 4 down, we're going to have negative 4 on the y part of the vector. And that there fully describes the single transformation that takes place between f of x and g of x. Okay, so for part CII, what we're asked to do is find the range of the function h of x. So we're given another function here, which is 21 over 2x plus 4x plus 9. And what we're really seeing here is that we've got 21 over, again, if we remember this from the previous part of the question, this is just f of x. And by range, what we really mean are the smallest values that h of x can be and the largest values of h of x can be, and creating an inequality where we've got a number here and a number here, okay? And now let's dig into this a little bit deeper. What we've got is a fraction, okay? And this fraction is going to be greatest when f of x, okay, so the denominator is the smallest, okay? And if we look at what we've got in terms of f of x, I think the most sensible way to approach this is if we use the completed the square form. And now we really need to ask ourselves, okay, when is this the greatest and when is this the smallest? Okay, this here is greatest, okay, when x is as large as possible. And when x tends towards infinity, it's clear that f of x will also tend towards infinity. So the highest value of f of x, in other words, the sort of range of f of x, the highest value of the range is infinity. The lowest value that this could be, okay, and given the fact that this has to be positive, okay, because what we've got is an x plus 1 squared term, which is always positive, times by 2 plus 7. The smallest value of this is incidentally going to be 7. Because what you do is you substitute such a value where you've got this equaling 0, 2 times by 0 is going to be 0, and you add 7 onto that. So incidentally, the range of f of x is going to be between 7 and infinity. And what we really need to do is we need to use this range here of f of x to find the range of h of x. H of x, like I've mentioned so far, will be greatest when f of x is the smallest. So the smallest value of h of x is going to be 21 divided by 7, which is equal to 3. And the largest value is going to be 21, or the smallest value is going to be is going to be 21 over infinity, which is going to be something incredibly close to 0. Mathematically, it is defined as 0. Okay, so this gives us the smallest value of h of x and the largest value of h of x. Okay, and the answer to this is going to be 0, h of x, and 3. So h of x can be is greater than or equal to 0, but less than or equal to 3. This is its minimum and maximum value, and hence this is the range. And that's the answer to that question.
For question number 6, we have a really nice trigonometry question. So we've got 5 sine 2 theta equaling 9 tan theta. And what we're asked to do is to solve for theta between minus 180 degrees and 180 degrees, giving answers to 1 decimal place. So with this, what we've got here is we've got a double angle here. So we've got sine 2 theta, and we've got obviously a tan theta term here. So really what we want to be thinking of is the sort of double angle formula that we're given, and they are in your formula book, although we really do sort of recommend you to memorize them, because you'll need to use them with obviously such high frequency in the exam. So you get 5 times by 2 sine theta cos theta, which is the double angle formula for sine 2 theta. And that there obviously equals 9 tan theta. But what I really want to stress here is this idea that when you've got sine theta terms and cos theta terms, and with perhaps an odd tan theta term, what you really want to be doing is turning that tan theta term into sine theta over cos theta. So I'm just going to apply that into there. So what we've got here now is sort of all of this sort of equation in sine theta and cos theta terms only. So I'm just going to multiply this out. And what we can find is that we can cancel a few terms out here. This sine theta cancels out with that sine theta. And we can get that 10 cos squared theta equals 9. And from that we can gather that cos squared theta is equal to 9/10. And now what we really need to do is try and find this theta term on its own. So I'm just going to square root cos squared theta. So what you get is just the cos theta. And that's going to equal plus and minus 9 over 10. And remember that plus or minus, because that is the key to being able to obtain all the solutions to the equation between minus 180 degrees and positive 180 degrees. And now what I'm going to be doing here is just going to be finding out sort of the, I'm just going to be finding out values for theta. So I'm just going to be doing an arc cos of positive 9 root 10 first. So positive 9 root 9 over 10 first, and that will give us 18.4 degrees. Okay, and now what I'm going to be doing is I'm going to be doing the same thing but to the negative. and the negative will give us 161.6 degrees. Okay? But what we really need to realise is that there are other solutions that are equivalent to these angles that are within that range as well. So for that, what I'm going to be doing is I'm going to be using the help of a handy cast diagram. Okay. For this one here, because we had obtained a positive root 9 over 10, we're going to be sort of focusing on these regions here. So what we've got is we've got 18.4 here. And the equivalent solution in the negative part, so from minus 180 degrees to 0 degrees, is going to be negative 18.4 degrees, okay? Because you're going to be going this way around the cast diagram, which provides us our negative solutions. For this one here, because what we had sort of calculated was the arc cos of a negative root 9 over 10, for our next cast diagram, what we're going to focus on are the regions of the cast diagram for which cosine is negative, and that's going to be this region here and this region here. So what we've got is we've got 161 degrees, 0.6 degrees, and the equivalent negative solution will be the other way around. So what we're going to be getting is a negative 161 degrees, negative 161.6 degrees. And these here are our 4 solutions, which would give us our sort of 6 marks. So these here will give you all the marks for this question. Part B is to deduce the smallest, right? So the smallest positive solution. Okay, remembering that's the key part of the question here. To the equation 5 sine 2x minus 50 degrees equals 9 tan x minus 25 degrees. Now what we really want to be doing here is looking at the sort of similarities between the two. Okay, and quite simply what we can see is that they've sort of switched theta for x minus 25. Okay, so here they have times x minus 25 by 2, which gives us that 2 theta value, and 2x minus 50 degrees here. And x minus 25 has just quite simply been interchanged for theta there. So what we really want to be doing is we want to be finding such a value that we can substitute here one of these 4 that would enable us to get x, okay, once we've added 25 to whatever value we select here out of these 4, that would give us the smallest possible solution, okay, the smallest positive solution. And just selecting, or just using sort of common sense here, it's clear to see that this value here would give us the smallest positive solution. So if we were to put minus 18.4 degrees here, add 25 to the other side, we're going to quite simply get the right answer and bring to 1 decimal place, which is required by the question, of 6.6 degrees. And that's the answer to that question. In question 7, we are told that in a simple model, the value V in pounds of a car depends on its age, T, in years. The following information is available for car A. First piece of information that we're given is the fact that its value when new is £20,000. In other words, its value, okay, so V, when T is 0, is £20,000. Secondly, we're told that its value after 1 year, okay, so its value V when T is 1, is £16,000. So we're going to have to sort of remember this information. We're going to have to apply it when we, in part A, use an exponential model of the form for car A, to find a possible equation linking its value with the amount of time since this sort of model is being applied. So in A, what we're really asked to do is come up with an exponential model. And when it comes to the sort of derivation of this model, what we really need to understand is that there are almost 2 types of exponential model that we can create. So we can have V equaling some constant A multiplied by e to the power of k times by t, where k is a constant. So you've got v equaling a, which is a constant, multiplied by e to the power of k times t. Equally, we can also have another type of exponential model where we have v equaling a multiplied by some constant r to the power of t. Now, personally, what I recommend is whenever you're sort of asked to come up with an exponential model, always use this one here. And the reason why you use this one here is because you're able to use LUNs. And as we will demonstrate, the use of LUNs is a very positive and very sort of encouraging way to approach such a question. So what we're told here, okay, and I'm going to sort of apply my previous reasoning, is that its value when new is £20,000. So its value, okay, and I'm going to take v here as the value, is equal to some constant a. And remember, so its value when new, so t is going to be 0, so it's going to be e times k to the 0, which is e to the power of 0, which is 1, okay? So we get here that 20,000 equals a times 1, which means that obviously a is equal to 20,000. Now we're going to use a second piece of information now, and that states that when t is 1, okay, the value of the car is 16,000. So what we're going to be getting here, and I'm going to be using the value that we got from a, or of a, from the previous question, from the previous part of the question, and we're going to be multiplying that by e to the power of k, because t is 1 in this case. So what we've got here is this sort of equation here that we can sort of get this k value from, since that is the sort of second unknown that we're trying to work out, the second constant to this possible equation that we've created. And now I mentioned that we use e because it ultimately allows us to use LUNs. So what I'm going to be doing is I'm going to be getting LUNs of both sides. So we get ln of 16,000 here, equaling ln of 20,000 here. Okay, e to the k. And then we're going to use here we're going to be using our logarithmic laws. So wherever we've got an expression that's being multiplied and a particular logarithm of here, in this case a logarithm of base e, what we're able to do here is put it in such a way where we can say that this expression here is ln 20,000 plus ln e to the k. And I'm going to be using the second sort of logarithmic law here in saying that because we've got a power here, we're able to bring that down such that this ln e to the k becomes k ln e. And as we know, ln e is going to equal 1, so we can quite simply cancel that out. And that gives us k equaling ln 16,000 minus ln 20,000. And now what I'm going to be doing is I'm going to be applying yet another logarithmic law, the subtraction law, such that k is going to equal ln 16,000 over 20,000. And we will find that the answer to that, which will give us ln, I'm going to give it in approximately 3 significant figures, is going to be minus 0.223. And that gives us the equation that v is equal to 20,000, which is our a value, multiplied by e to the power of minus 0.223 t. So we're given a bit more information here that will allow us to sort of, approach part B. We're told that the value of car A is monitored over a 10-year period. Its value after 10 years is £2,000. Evaluate the reliability of your model in light of this information. So really what we want to be doing here is we want to be substituting 10 into there. So we can find out what our model would suggest the value should be after 10 years. And that gives us an answer, remembering it's in pounds here, of 2,150. And because the question states that the value of the car after 10 years is £2,000, it's clear that to one significant figure at least, the value that the model is suggesting is rather close to the value, or to the actual value. Therefore, we can state that because 2,150 sort of approximates to £2,000, it suggests, okay, remembering that key word there, suggests, okay, so it's not empirical, shall we say, it's suggestive of the fact that the model is reliable. Okay, let's look at part C now. Explain how you would adapt the equation found in A so that it could be used to model the value of car B. And car B is sort of illustrated with this information here. Firstly, this car B has the same value when new. So in other words, this A value that we've calculated when t is 0 will remain the same. So in our new model, what we're going to be doing is we're keeping this the same. But what happens is the value depreciates more slowly than that of car A. So ultimately what we're going to be doing here in this model is we're going to be keeping this the same, so there'll be no change made to the A constant. However, the sort of rate of decrease, in other words, the K value that we found out here, will almost be less negative. In other words, it would be negative still because the car is still depreciating in value. However, it won't be as negative. It's going to be greater than minus 0.223. So what we can say here is that what we're going to be doing is adapting the model such that K, and in brackets here we're going to put minus 0.223, becomes greater while still being negative. Negative. In other words, making it less negative. And that there is the answer for question 7. In question number 8, we are given figure 2, which shows part of the curve with equation y equals x plus 2 multiplied by x minus 4. So in essence, what we're given here is a cubic curve, a positive cubic curve, that the question is quite handily sort of factorised for us. And we're told that the region R1, shown shaded in figure 2, is bounded by the curve and the negative x-axis. And what we're asked to do is show that the exact area of R1 is 20 over 3. So really our first step with this is going to be to put this in a form where we're able to integrate it. And obviously the first the first thing that comes to mind is just going to be to expand this out. So we've got x plus 2, and then we've got x minus 4. So first what we're going to be doing is just going to be expanding these two out. That gives us x squared plus 2x, and we're going to be multiplying that by x minus 4. That gives us x cubed minus 4x squared plus 2x squared, which is minus 2x squared, and then minus 8x. Okay, and that's our y term. And now what we're going to be doing here is we're going to be integrating this, okay? And really what we're going to be doing is integrating this with respect to x. And that should give us x over 4 minus 2/3 x cubed. And then here what we're going to be getting is adding 1 to the term, then dividing by that 4x squared. Now, what we're asked to do is show that the exact area of R1 is 20 over 3. And now what we really need for this is are the sort of the limits essentially of our integrated expression. So what we need is the root here and the root here. Now the question is, as I've said, quite handily factorised the function for us. So we can see that from this first term, okay, that that this is going to give us 0. And from the second term here, this root here is going to be minus 2. So what we really want to do is our limits of our integral are going to be between 0 and minus 2. Now, if we were to put 0 into this, we'd get 0. So what we're going to be doing is we're going to be doing 0 minus, and whatever we get when we substitute minus 2 into the x here. And that's just going to be the same as doing a negative, or negating what we get when we substitute minus 2 into our integrated expression. So wherever we see an x here, I'm just going to substitute our minus 2 into that. And what we get from this, okay, is 20 over 3. If you were to plug this into your calculator, you'd get 20 over 3. And that there completes part A. For part B, okay, we have to sort of digest some more information here. We're shown that the region R2, so this region here, okay, below the x-axis, okay, and that's going to be quite important as we move on with the question, also shown shaded in figure 2, is bounded by the curve and the positive x-axis, and aligned with equation x equals b, where b is a positive constant. Given that this area here, R1, is equal to the area of R2, we're asked to find that b satisfies the equation that we can see here. Now, with this, what we really need to do is we really need to sort of integrate, or sort of, now that we've integrated our expression by sort of through the process of integration here, we need to change our x limits such that we're finding the area of R2 and equating it to R1, which was 20 over 3, which we determined in part A. So what we're going to be doing is going to be sort of changing our limits to b and 0, because that's the region that is, or those are the x values that act as the limits for R2. And that there we're going to set equal to 20 over 3. Now we already know that if we were to sort of put 0 into this, we'd get what we'd get is 0. So what we really need to be doing is just need to be focusing on the b. So we're going to be substituting b into this here, and we get b to the power of 4 over 4 minus 2b cubed over 3 minus 4b squared, and that's equal to 20 over 3. Now what I really want to be doing, actually one important thing to understand is that since this is below the x-axis, we're going to be getting a negative 20 over 3. Okay, and that does change the answer. Now, in order to get rid of these fractions, what I'm going to be doing is I'm going to be timesing all of these terms. I'm going to be timesing all of these terms by a number that has 4 and 3 as factors, and that's going to be 12. So I'm going to be timesing this by 12, that by 12, that by 12, and that by 12. And what I should get is that 3b to the power of 4 minus 8b cubed minus 48, 12 times minus 4 is minus 48, b squared equals, and if I was to times this by 12, I'd get minus 80. So now we've got an expression where we've sort of got rid of some messy fractions, and since the expression we've got here, or this equation that we've got here, is equal to 0, I'm going to be just sort of moving this to the other side to make this also equal to 0. Brilliant. Now, in terms of taking this and manipulating it in such a way where it becomes this. There are two ways in which we can approach this. Firstly, what we can do is we can sort of factorize this out. This is quite messy. It will involve all sorts of polynomial division and the likes. Or you can quite simply just expand this out and say that it's fundamentally equal to this. So what I'm going to be doing is I'm going to be using the second way. Yes, it is quite cumbersome, and yes, it is quite arduous, but ultimately it would allow us to get to the answer in a much more simple way. So I'm going to be expanding this out. So the expression above was b plus 2 squared multiplied by 3b squared minus 20b plus 20. I'm going to be expanding this out first, and that should give us b squared plus 4b plus 4, and that is multiplied by 3b squared minus 20b plus 20. And just remembering the fact that this is equal to 0. And now I'm going to be sort of multiplying this out. So sort of term by term, just making sure that each term is being multiplied in this expansion. Okay, so when we've got these three terms, these expansions can get a little bit messy, but it's important just to ensure that you're drawing these lines to keep sort of track as to what terms you've expanded and what terms remain. So doing that, I'm just going to be sort of doing that in. So you get 3b to the 4 minus 20b cubed plus 20b squared plus 12b cubed minus 80b squared plus 80b plus 12b squared minus 80b plus 80. So as you can see, it does indeed get quite messy. And now what we're going to be doing is we're just going to be sort of tidying this up. And what we'll get from that is that 3b to the 4, that remains, so we can cancel that out there. I'm going to head and cancel out all the cubic terms that I'm going to gather and collect. So we get here that it's minus 8b cubed. I'm going to be cancelling out all these square terms, and that works out to minus 48b squared. And then, of course, what we've got here is minus 80 plus 80, which cancels out, and we've got 80 left. Okay, and that equals 0. And what we've found here is that this here, quite conveniently, going to be equal to this here. Okay, and hey presto, we've verified that B satisfies this equation. Okay, so for part C, what we're asked to do is explain, with the aid of the diagram, the significance of the root 5.442. Okay, and to understand this question, what we really need to do is sort of take in this information here. We're told that the roots of this equation, 3b squared minus 20b plus 20, are 1.225 and 5.442 to 3 decimal points. And the value of b is therefore 1.225 to 3 decimal places. Explain with the aid of a diagram the significance of the root 5.442. So technically what this is showing us is that there are two values of b such that if you were to complete the limits between 0 and that b value, you'd get this sort of equation, or this area here, when you put it into when you substitute them into the integrated expression. The first value, which is the value that we've sort of been dealing with so far, is 1.225. But what this is saying is that there is another value of b. So if I was to get this line and shift it further, I'm just going to draw a line there to help sort of signify that. Okay, so there is another line here supposedly where x equals b, and this here is going to be equal to the second value of b, which is 5.442, such that the combination of this area here and this area here, imagining that the curve is going up, is going to be 0. So, as you know, when you're integrating a curve or an equation that goes, or that is both negative and positive, when you're integrating it across both negative and positive parts of the graph, the negative and positive parts will tend to work against each other. And in this case, what they will inevitably do when you're finding out the integral between the limits of 5.442 and 0, these parts of this integral will cancel out. And what that will leave is this area here, R2, which is equivalent to R1. And that really is it. And this area and that area, areas will be the same. So if they are to cancel out, this negative area here will meet this positive area here of the same magnitude, of the same size, and the two will cancel out. Size/area. And that there is the answer to question number 8. For question number 9, we are told that given that A is greater than B, which is greater than 0, and that A and B satisfy the equation log A minus log B equals log A of A minus B, show that A equals B squared over B minus 1. So it's clear that with this, what we're going to be having to use are sort of log rules and applying those in such a way where we're able to manipulate this such that it becomes this. So instantly we can see that what we've got is we've got a subtraction between logs, and with that what we can use is the subtraction rule, so that log A minus log B is the same as log A over B, and that's going to equal log A minus B. And since now we've got logs with the same base 10, on both sides of the equal sign, we can actually get rid of the log, such that A over B equals A minus B. And what I'm going to be doing now is I'm just going to be sort of multiplying this by B. And now what I'm going to be doing is I'm going to be combining like terms. I'm going to be factorising out the A. And I'm going to be taking this to the other side to make A the subject. Brilliant, that's exactly what's required there. And for part B, we're asked to find, or to write down the full restriction on the value of B, explaining the reason for this restriction. So to gather the full restriction for B, what we're going to have to do is link it back to the beginning of this question, in which we're told this set of facts here. We're told that A is greater than B, which is greater than 0. And as A is greater than 0, it's incidentally true that this expression here, b squared over b minus 1, which is equal to A, must also be greater than 0. And now for this to be greater than 0, in other words, for it to be positive and not equal to 0 itself, it's clear that B cannot be 1. If B was 1, what you'd find is you've got a circumstance where you've got b squared over 0, which will be 0, not greater than 0. So B cannot be equal to 1. At the same time, we just need to stress the fact that this has to be positive. The numerator, b squared, will always be positive. If b is greater than 0, as put here, even indeed if it was negative, as long as b is a non-zero number, b squared will always be positive. b minus 1, however, can be negative, and if it is negative, this whole expression will become negative. So it's clear that the denominator then in that case must be greater than 0. The denominator has to be positive for this whole expression to be positive. And what we can do is we can just take this 1 to the other side and discover that b has to be greater than 1. And that there, quite simply, leads us to the sort of answer. If b cannot be 1, it's clear that b has to be greater than 1, and this here, we can get rid of this and just describe this as the full set of restrictions on the value of b. So b can be sort of anything greater than 1 in this case. And that there is the answer for question 9. For question number 10i, we are asked to prove that for all n natural numbers, so all positive integers, n squared plus 2 is not divisible by 4. So for any positive integer that we put into n here, n squared plus 2 will not be divisible by 4. Now, the key to sort of answering this question correctly is to prove that it's the case for both odd and even numbers. So we're going to start by proving that it's true for even numbers. So to denote even numbers, what I'm going to do is I'm going to say that n is equal to 2m. Okay, and this 2 here, like anything multiplied by 2, will mean that this expression as a whole, okay, is even. And I'm going to be just putting it into the equation here. So I'm going to put in 2m where I can see n, and that is equal to 4m squared plus 2. And I'm going to go ahead and try and divide it by 4. And what we can see is that this divides quite nicely, but this here becomes 2 over 4, which in other words is a half. And what this means is that we've got a remainder of a half, which means that for all even numbers, n squared plus 2 is not divisible by 4. Now we need to do the same for odd numbers. And to denote odd numbers, what we do is we take this even number and we add 1 to it. Okay, because all odd numbers are in effect an even number with 1 added to them. And what I'm going to be doing is I'm going to be doing the same thing and substituting it into the sort of equation there. 2. Just going to expand that out. Plus 1, plus 2, get plus 3. And I'm going to go ahead and try and divide this all by 4. And again, this divides nicely, this divides nicely, but this here, what we end up with is 3/4. So what we get is that there's a remainder of a half and 3/4 respectively for even and odd numbers. I'm just going to put that down in sentence. Odd numbers. Hence, okay, and then what we're going to put in here is that for all positive natural numbers, n squared plus 2 is not divisible by 4. Okay, and that answers part I. For part II, what we're told is that given that x can be any real number, okay, so we're given a lot more freedom this time, where it can be any real number, any non-imaginary number, which obviously you don't really go into unless you're doing further maths, the value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. State, giving a reason if the above statement is always true, sometimes true, or never true. Okay, it's clear that it is, in most circumstances, true. So if I was to put, 1 into this, 1 times 3 minus 28 is going to equal minus 25, and the modulus of that is going to be 25. And if I was to put 1 into this, I'd get minus 8. Okay, and obviously 25 is greater than minus 8. But what I really want to do is I want to pay attention to really the essence of the numbers here. I want to try and make this as small as possible, or as close to 0 as possible, because we've got a modulus here. Even if we do have a large negative number, very, very, very small number, what will end up here is a very large number, because what this will do is it will remove that negative sign. So we want the number to be as close as possible to 0. So say if I was to times 9 by 3, what I'd end up with is 27 minus 28, which is minus 1. Okay, and the modulus of that would be 1. And that would be a number that is incredibly small, but not small enough. Okay, so what I really want to be doing is I want to be playing within that range of 9, maybe between 9 and 10, and I want to be sort of playing with those numbers, substituting them in, and coming up with, in other words, a contradiction to this statement that would enable us to prove the fact that it's sometimes true. Okay, we know that it's true in some occasions. We've just demonstrated that when we've put 1 in, so it's not going to be the case that it's never true. But we really want to explore the case that it could be sometimes true. And to do that, what I'm going to be doing is I'm going to be substituting again a number between 9 and 10 in. We're going to try 9.4. Okay, so the modulus of 3 times by 9.4 minus 28. Okay, and what I'm going to be doing is I'm going to be putting that into a calculator. And what we get is the fact that it's equal to 0.2. And what I'm going to be doing is I'm going to be doing the same here. Okay, so we've got 9.4 minus 9. Okay, and we can do that without a calculator, and that's going to be equal to 0.4. And what we found is that in this particular circumstance, when x equals 9.4, the value of this here, x minus 9, is greater. Okay, is 0.2 units greater than the modulus of 3x minus 28. So it really is just a case of looking at these questions, trying to identify patterns. In this case, it was acknowledging the fact that because this is a modulus sign, we want to get this as close as possible to 0. And it really is just using those patterns to come up with a contradiction. You need to play around a little bit with those sorts of questions, but bear in mind also that it is 2 marks. So if you do find yourself spending perhaps too much time on these questions, do feel free to perhaps leave it and come back to it at the end. So yeah, what we can see is the fact that it's sometimes true. Okay, and that there is the answer for question 10. In question 11, we are told that a competitor is running a 20-kilometre race. She runs each of the first 4 kilometres at a steady pace of 6 minutes per kilometre. After the first 4 kilometres, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometre is going to be modelled to be 5% greater than the time that she took to complete the previous kilometre. So in a strange way, what we're ultimately going to be getting here is a geometric sequence where each term of this sequence after the initial 4 kilometres is going to be increasing by 5% with a common ratio of 1.05. Okay, and remembering that 1.05 is the multiplier for 5%. And what part A is asking us to do is, using this model that's being described here, show that the time to run the first 6 kilometres is estimated to be 36 minutes and 55 seconds. So what we need to do is that we need to add, okay, the first 4 kilometres, which are being done at a steady pace of 6 minutes, to the fifth kilometre, which is going to be 6 times 1.05, 5% greater than the 6 minutes taken to complete the 4th kilometre. And the 6th kilometre is going to be 1.05 times whatever we'd calculated for the 5th kilometre. So doing that, what we should get is 6 plus 6 plus 6 plus 6, and that gives us the sort of total for the first 4 laps. And what we're going to do is we're going to add that, okay, now that the geometric sequence has begun, add that to 6 times 1.05, and what we're going to be doing is, for the next one, we're going to be timesing 1.05 by whatever we've got here, to ultimately get 6 times 1.05 squared. And what that does is it gives us a total value of 36.915 minutes. Okay, so we've got 36.915 minutes. So we've got 36 minutes, and these are our 4 minutes. And this 0.915 minutes, what I'm going to do is I'm going to times it by 60. And that will give us how many sort of seconds it is. And it's 54.9 seconds, and rounding that up to the nearest second, what we get is 55 seconds, as required there. For part B, we're asked to show the estimated time in minutes to run the half kilometre from the 5th kilometre to the 20th kilometre, because remembering the race itself is only 20 kilometres long. Can be given by this expression here. And to those of you that have got your sort of your series formulas and your sort of your sequence formulas and your nth term formulas memorized, this is the nth term of a geometric sequence. And what it does is it takes the initial value, the first value of the sequence, and bearing in mind that the value of the sequence, or that the sequence itself starts on the 5th term, or on the 4th term, sorry, and that's times by the common ratio, the power of n, whichever term that will be, minus 1, okay? And that gives us the nth term of a geometric sequence. And we're asked to show that her estimated time can be sort of given in this. And now we can't necessarily assume that this is true, otherwise that would make this question perhaps far too simple. Instead, what we're going to be doing is that we're going to be sort of using examples of laps and demonstrating how we can demonstrate. Or how this ultimately equals the estimated time in minutes of that particular kilometre. So what we can really try and do is try and work out the sort of 5th, 6th and 7th kilometre, and really sort of try and apply that to what we've done so far. So the 5th kilometre is obviously going to equal 6 times 1.05, which again is going to be 6 times 1.05 times 5 minus 4, which is going to be to 1, and indeed we can see that both sides of this match. The 6th kilometre, which is what we're determined here, is going to equal 6 times 1.05 times by 1.05, which when we apply it into this here is going to be 6 times 1.05 to the power of 6 minus 4, which is 2, and again sort of matching up to what we've got there. It indeed applies for the 6th kilometre, and we're just going to sort of apply it for the 7th kilometre now, just to sort of summarise this. And what we'll find is 7th kilometre is going to be 6 times 1.05 times by 1.05 times by 1.05, and that will equal to 6 times by 1.05 cubed, okay? And indeed that applies to both sides of this particular proof here. And hence, I'm just going to put the sort of last sentence here, hence the time taken for the, and I'm going to use their language here, half kilometre is equal to 6 times 1.05 times r to minus 4. Okay, And now for part C, what we're asked to do is we're asked to sort of attempt to find out the total time in minutes and seconds that it will take to complete the race, and just bringing it back to focus that the race in itself is 20 kilometers long. Now, to complete this, what we're going to be using is the series formula. So what we're going to be doing is we're going to be adding these here, and these are terms, or these are kilometers in which the sort of geometric sequence hasn't applied. And what we're going to be doing is we're going to be using the formula for the series of a geometric sequence, which is going to be the first term multiplied by the common ratio subtracted 1 over the ratio subtracted 1. Remember, this ratio is to the power of however many terms we want to work out. And in this case, because we've worked out the first sort of 4 kilometers already of the race, we're going to be using this series formula for the remaining 16 of the 20 kilometers of the race. And I'm just going to be substituting the numbers in now. So we know that 6 times 1.05, which is in essence almost the first the first term of the sequence, and that equals 6.3, and we're going to be timesing it by r, which we had illustrated to be 1.05, our percentage multiplier that shows that each subsequent kilometre after the 4th is taking 5% longer to complete. And we're going to be putting that to 16, since it's 16 kilometres following the first 4 that we're applying the series formula to, subtracting that over 1. And what we're going to be doing then is we're going to be subtracting r minus 1, so 1.05 minus 1. And what that gives us is approximately 173 minutes and 3 seconds. And that there is our answer. For question number 12, we are given a function, f of x, which equals 10e to the power of minus 0.25x multiplied by sine x. For part A, we are told to show that the x-coordinates of the turning points of the curve with equation y equals f of x satisfy the equation tan x equals 4. And because we're asked to find out the x-coordinates of the turning point, okay, these are the turning points here, what we're going to be asked to do is in essence work out the gradient of these turning points, or the gradient is going to be 0 at these turning points, and wherever the gradient is going to be 0, in other words, when the differentiated equation is going to equal 0, those points are the subsequent x-coordinates. And what we're going to identify is the fact that these x-coordinates satisfy the equation tan x equals 4. So what we're doing is we're going to be differentiating the function. So f of x is equal to 10e to the power of minus 0.25 x sine x. And to differentiate this, to work out f prime, what we're going to be doing is we're going to be sort of using the product rule. So in order to do that, what we're going to be doing is we're going to differentiating this term, this part of the function, and multiplying it by sine x. And then we're going to be adding that to the derivative of sine x, and we're going to be multiplying that by 10e to the minus 0.25x. So to work out the derivative of this part of the function, what we're going to be using is the chain rule. So we're going to be multiplying this by this, and then we're going to be keeping this the same. And that's going to be equal minus 2.5 e to the minus 0.25x. Okay, and we're going to be timesing that by whatever's here. We're not going to be doing anything to this. And we're going to add that to the derivative of this times by this. And this time we're not going to be doing anything to this. And the derivative of sine x, as you should know now, is cos x. Okay, and we're going to set this equal to 0. So what I'm going to do, I'm going to move this to the other side. So what we get is 10e to the power of minus 0.25x cos x equaling 2.5e to the power of minus 0.25x sin x. Okay? And because we've got e to the power of minus 0.25x on both sides of the equation, what I'm going to be doing is I'm going to be quite simply cancelling it out. Okay, and that gives, well, that takes out the bulk of the mess of this equation. And what we have left is 10 cos x equaling 2.5 sin x. I'm going to be getting the trigonometric function, so cos x and sin x on this side and the numbers on that side. So 10 divided by 2.5 is equal to sin x over cos x. And 10 over 2.5 is 4. Sin x over cos x, you should know now, one of the first trigonometric identities that you learn in AS maths. Sin x over cos x is equal to tan x, and 10 divided by 2.5 is equal to 4. And there we go. We have proven that the turning points, or the x-coordinates of the turning points of this particular function, satisfy the equation tan x equals 4. Now, for part B, what we're asked to do is to sketch the graph of h against t, where sort of the modulus is being taken this time. So h of t is actually doing the modulus of whatever f of x was. And we want to show the long-term behavior of this curve. In other words, what we're going to be doing is we're going to be on the next page doing the modulus of this curve here. And in order to work out the modulus, when the modulus signs are outside of the whole function, what we're going to be doing is we're going to be deleting any parts below the x-axis after we have sort of reflected them in the positive x-axis. So what we should be left with is something that looks a little bit like this curve here. So if we can imagine a sort of ball, okay, this is in the next part of the question. So when a ball has been kicked, when it's sort of bouncing around, it's going to get smaller and smaller in height after each bounce. So the function itself, once we've drawn this, should look a little bit like that. So what I'm going to be doing here is just going to be finding where we should be drawing this here. I'm going to be just sort of applying the axes here. And what I'm going to be doing is y, x, and applying that sort of same modulus curve there. So what we're going to be doing is we're just going to be drawing this here. Okay, and just ensuring that after each bounce, the curve gets smaller and smaller in height. Okay, and that there is that should suffice for a brief sketch of this particular function here. And for part C, we're told that this function here, ht, is used to model the height in meters of a ball above the ground t seconds after it's been kicked. Using this model, find the maximum height of the ball above the ground between the first and second bounce. So, in other words, this point here, okay? And what we're going to be having to do here is we're going to have to find the turning point, okay? But what we're going to be getting is, right, we found out that the turning points, the x-coordinates, in other words, this here shouldn't be x as much as it should be t. We're going to find out that the t-coordinate, or the t value for which the ball is peaking at its highest, is going to also satisfy this whole tan x, in this case tan t, equaling 4. Okay, so if we worked out the inverse tan of 4, which should give us our sort of value of t, and I'm going to be using radians here, although it doesn't matter if you use radians or degrees, because ultimately what you're going to be doing is finding the value of this function regardless of what your input is, okay? And between degrees and radians, as long as you keep your use of them constant throughout the input of the function, the value of the function at the end should be the same regardless. So if we were to inverse this, what I'm going to get is 1.33 radians. okay? But what that does is it gives us the first positive value, okay? So this here, right, would be 1.33. That's going to be the value of t, but that's going to give us the highest point between this point here, okay? But what we want is the sort of the value of t, the highest point, okay, at which the highest point that t offers between the first bounce and the second bounce. So if you can imagine the ball coming in like this, bounces once, bounces twice. Between this first bounce and the second bounce, we're after this t value here that gives the highest value of h of t. And to do that, we need to remember the fact that the tan graph repeats every pi radians. You can use the cast diagram, and what we'd do for this is we'd do sort of 1.3 radians here, 1.33 radians here, 1.33 radians here, and what you do is just add on pi to 1.33 radians in order to give us this sort of angle here, this angle here. But what we're going to be doing is just going to be using, without the use of a cast diagram, just adding pi radians on here, using the fact that the tan graph repeats every pi radians. So 1.33 plus pi is going to equal to 4.47. Okay, and what I'm going to be doing now is I'm just going to be substituting it into here. So the value of h at that particular point is going to equal the modulus of 10e to the power of minus 0.25, 4.47. Okay, and that's going to be multiplied by sine 4.47. And I'm just going to be using a calculator for that. And what we get is a value of 3.18 meters. Okay, and I'm just going to check that it is meters. Okay, it doesn't make clear that it's meters, so I'm just going to go ahead and get sort of rid of that there, and just keeping the height as 3.18. And that there is the answer for question number 12. For question 13, we are given the curve C with equation y equals p minus 3x over 2x minus q over times x plus 3, where p and q are constant. And what it does is it passes through the point with x coordinate 3 and y coordinate 1/2. And we're told that it has two vertical asymptotes, in other words, points where the graph reaches a value of infinity with equations x equals 2. So when x is going to equal 2, we're going to be seeing a vertical asymptote there, and when x equals minus 3. So another vertical asymptote there. And for part AI, what we're asked to do is explain why we can deduce that q equals 4. So what we really need to do is sort of pick this this equation away really with what we can gather from it. And fundamentally, really, I just want to bring up what I mentioned previously. For this vertical asymptote to occur, what you really need to see is the value of this equation hitting infinity. And there really is only one way it can do that, and that's if the denominator is equal to 0. Now this can happen either when 2x minus q is equal to 0, or when x plus 3 is equal to 0. So the sort of asymptote at x equals minus 3 will occur when this is equal to 0, because what you can see is that when you substitute minus 3 into here, this part of the denominator becomes 0. And what that really leaves is this x equals 2 asymptote occurring when this equals 0, when 2x minus q equals to 0. And what we can really do there is just solve a very simple equation. So what I've done is I've substituted the 2 there because that's where the asymptote occurs when this is 0. Okay, so we've set that equal to 0. And then just sort of what we get is quite simply that q is equal to 4. Okay, and that's enough to sort of achieve the mark that you'd get for that question. For part II, what we're asked to do is sort of take that further, almost using the fact that we know now that Q equals 4, to show that P is equal to 15. And what I'm going to be doing there is I'm going to just be sort of putting in 4, since we now know that as the value, and substituting the x coordinate as 3 and the y coordinate as a half, since we know that it does pass through 3 in half. So I'm just going to be doing that. So the equation itself is y equals p minus 3x over 2x minus 4 multiplied by x plus 3. And again, what I'm going to be doing is, because I've already substituted our value for q in there, I'm just going to be putting the coordinates that we know it passes through, so 3.5 in. Okay, so we get that a half is equal to p minus 3 times, and the value of that coordinate that passes through was 3, so p minus 3 times 3, which is p minus 9, over 2 times 3, which is 6, minus 4, that's 2, multiplied by 3 plus 3, which is going to be 6. So we're getting 12 here. So then we know that p minus 9 is going to equal 12 times a half, which is equal to 6, and hence p is going to equal 15. Okay, so what we've done there is answer part I and II of part A. And what we're going to be doing now is moving on to part B. Quite a big question. It's an 8 marker, but I really do assure you that whenever you do come across these big questions, sort of just try and focus on it bit by bit, try and break it down, and ultimately confront what you have. Don't be scared off by the big number there. So we're told that figure 4 shows a sketch of part of a curve of part C, of curve C, and the region R shows sort of the curve being bounded by the x-axis and x equals 3. So for part B, what we're asked to do is show that the exact value of area R is A ln 2 plus B ln 3, where A and B are rational constants to be found. In other words, they're not decimal points that go on and on and on, and equally they can be negatives as well. So what we really need to do now is integrate. Okay, so we need to integrate our expression here. We know what the value of P is, it's 15. We know what the value of Q is, it's 4. And what we really need to do is we really need to sort of integrate that. But to integrate it and to get the sort of the area of region R, what we really need to know are the limits. So the lower limit is obviously going to be 3, because we're told that the region R is bounded by the equation x equals 3 on the x-axis. But what we really need now is the value of x here. And the value of x here is going to be when the equation that we have here is going to be equal to 0. Okay, so that's the first thing I'm going to be calculating. So I'm just going to be substituting our value of P and Q in that we've already determined, so we're not stuck with any unwanted unknown constants that we now know. And I'm going to set that equal to 0. Obviously, taking this to the other side, that's all going to become 0. So we're going to get 15 minus 3x equals 0. 15 equals 3x, and henceforth x is going to equal 5. So therefore we know now that this here is 5. And the exact sort of area of R is going to be the integral between the limits of 5 and 3, the whole of the equation that we can see previously. And that's going to be 15 minus 3x over 2x minus 4 multiplied by x plus 3. Now, this here is sort of impossible to integrate in the form that we have in currently. So what we really want to be doing is we want to be turning this into 2 separate fractions. And you really do sort of approach this topic at the start of your A2 part of the course. And what we're going to be using are partial fractions. So what we're going to be doing is we're going to be sort of, again, finding the integral, but what I'm going to be doing is I'm going to be sort of splitting this into 2 fractions. A is at one numerator over 2x minus 4. I'm going to add that to B as the second numerator over x plus 3. Keeping those in brackets. And just remembering the fact that this is obviously integrating with respect to x. And what I'm going to be doing now is solving values for a and b. So we know now that 15 minus 3x over 2x minus 4 multiply it by x plus 3 is going to equal a over 2x minus 4. And really we should be using this here because we should be able to plug in any value of x and get the same on both sides. So we're going to be using this here, this identical symbol. And what I'm going to be doing now is just following standard protocol when finding values of a and b when solving partial equations. So 15 minus 3x is going to be identical to a, and then what I'm going to do is multiply this numerator or this denominator by this numerator here, and applying the same for b, so multiplying b by 2x minus 4. Make that clear. Okay, and what we're left with is this. Okay, remember we get rid of the denominator here. Now, what I'm going to be doing is I'm going to be substituting values in here that allow me to cancel a particular unknown, and then what's focusing on the other. So to cancel a, what I'm going to be doing is I'm going to be letting x equal minus 3. Okay, and I'm going to be substituting minus 3 here, so we get 15 minus 3 times minus 3, so that's going to be 15 plus 9, 24. And I'm going to be substituting minus 3 to this. Minus 3 plus 3 is 0. 0 times a is 0, so we get rid of a, and that means we're going to be focusing on b. So I'm going to be putting minus 3 into here, and what we get is 24 equals minus 10b. And then what I'm able to do is divide that by that, and find out that b is equal to minus 2.4. And now what I'm going to be doing is I'm going to be applying a similar technique for part A, and just need to think what x value I can put in here to cancel b out so I can focus on a this time, and that's going to be 2. So what I'm going to be doing is I'm going to be letting x equal 2, and then we get, when we substitute 2 into this part of the equation, we get 9, and 9 is going to be equal to 5a. So what we really get here now is that a is going to be equal to 1.8. Okay, so now we know now that finding the integral of this is going to be the same as finding the integral between 5 and 3 of 1.8 over 2x minus 4, and remembering now that this here is going to be a negative 2.4 over x plus 3. Okay, and now what we're going to be doing is we're going to be integrating each of these expressions. Okay, so to integrate this, we need to know that because we've got an x term here in the denominator, we need to apply a ln here, okay, and then we need to adjust the constant on the top. So we know that the integral of this is going to be ln with 2x minus 4 within the ln, and what we're going to have to do is integrate or manipulate the constant at the front. So I'm going to be letting I equal ln 2x minus 4, and if I was to differentiate this, what I'd get is I'd get 1 over 2x minus 4, and because I need to use a chain rule here, I'd have to multiply it by the sort of derivative of this here, which is 2, and I'd end up getting 2 over 2x minus 4. So that means ultimately what I need to do is I need to half this. So I need to half it in order to get the standard, in order to get just 1 over 2x minus 4 on its own. So what I need to do is I need to do 1.8 multiplied by a half times by ln 2x minus 4 to get the integral. A half times by 1.8 is going to be 0.9. Okay, and that's going to be 0.9 ln 2x minus 4. Here it's much more simple. Here the integral of this is going to be quite simply ln x plus 3, and we're going to times that by 2.4 in order to get the full integral for this expression. Okay, and that there is our integral. And obviously we know now that the limits here are going to be 5 and 3. Okay, so as we would with any other integration question, we're just going to be putting them in, sort of whacking them into here. Okay, and what we're going to be getting is 0.9 ln 6 minus 2.4, substituting 5 in here this time, ln 8 minus, and put it in brackets. Remember that, guys, always put it in brackets. And then it's going to be 0.9 ln 2 minus 2.4, oops, screen jump there, minus 2.4 ln 6. Okay, what I'm going to do now is just sort of multiply this minus 1 out, get rid of that pesky bracket, to get 0.9 ln 6 minus 2.4 ln 8 minus 0.9 ln 2 minus, plus here, because we've got minus times a minus, ln 6. Okay, now we've got that. Okay, now we've got this here. What we really need to do is start simplifying things down. Now this here isn't, unfortunately, isn't the end really when it comes to sort of having to manipulate things and having to simplify things. There really is more that we need to do. And the first step to realizing what we need to do is to read the question once more. And the question asks us to find the exact value of region R in this form here. Okay, so what it wants is, it wants the area in the form where you've only got ln 2 and ln 3 and multiples of those added together. So what we really need to do now is that we need to manipulate these in such a way, okay, where all we've got left are just ln 2s and ln 3s. Okay, so really what we need to do is, to understand that, we need to use our sort of logarithmic laws. So we know that ln 6 is going to be equal to ln 2 plus ln 3, because when you're adding two lns of the same, or two logarithms of the same base, you just multiply the number that each logarithm contains. So ln 2 plus ln 3 is going to equal ln 6. With ln 8, it's a little bit more complicated. 8 is the same as 2 to the power of 3, and here you're going to be having to use your index logarithmic law and take this to the other side. And this here is going to equal 3 ln 2. Okay, so using these two sort of laws here, okay, or these two applications of the logarithmic laws, what I'm going to do is I'm going to go ahead and manipulate these in such a way where we've only got ln 2s and only got ln 3s left. So I'm going to be doing that now. So we've got 0.9. Okay, and here we've got ln 6 and ln 6, and that's going to turn into ln 2 and ln 3. But we need to remember to keep this constant tagging along with each ln that this ends up becoming. Here, ln 8 becomes 3 ln 2. So what we're going to be doing is, in brackets there, ln 2. This here we don't have to do anything to it whatsoever, because that is already in a form of being in ln 2. And here, of course, what we have is 2.4 ln 6, and obviously that's going to break down into 2.4 ln 2 and 2.4 ln 3. Okay. And now what we're going to be doing is that we're going to be sort of really sort of trying our best in adding these together, and hopefully we've got a nice neat ending to this where we've got ln 2s and ln 3s each with a rational constant before them. So 0.9 ln 2 and minus 0.9 ln 2, they'll cancel out. What we're going to be doing is we're going to be adding 0.9 ln 3 and 2.4 ln 3, okay, in order to get 3.3 ln 3, and we're going to be getting 2.4 ln 2 minus 2.4 times 3 ln 2, and that will give us a value of minus 4.8 ln 2. And now what we've got here now is ln 3 and ln 2 with a constant that is rational before it, and that there is the answer to question number 13. Now, well done, guys. You've made it to the last question of the paper, question number 14. And in question number 14, we're given the curve C in the standard Cartesian plane. Don't be too scared by this. All this means that it's on a y-x axis as opposed to, say, a polar coordinate one. And it's defined by the equation x equals 4 sine 2y. And this curve C passes through the origin, so it passes through the point with x coordinate 0 and y coordinate 0. And for part A, what we're asked to do is find the value of dy over dx at the origin. Now, because what we've got here is x equaling 4 sine 2y, so in other words, what we've got is x here and some sort of function of y here. What's going to be easier is if we calculate dy over dx by doing 1 over dx over dy. So if we were to find the derivative of x with respect to y, what we're going to be getting is a particular expression that if we put 1 over that, we'd get dy over dx. And I'm just going to be doing that now. So for part A, dx over dy is going to equal to the derivative of this with respect to y, and that's going to be 8 cos 2y. And as I've mentioned, dy over dx is going to be 1 over this, which indicates that it is 1 over 8 cos 2y. And now we're asked to find the sort of value of dy over dx, the value of the gradient at the origin. So what we're going to be doing is we're going to be substituting 0 where we see y here, okay, in order to find out the value of dy over dx, because at the origin the sort of y coordinate is going to be 0. So at 0, 0, dy over dx is going to equal cosine of 2 times 0 is cosine of 0, and as you guys should know now, cos 0 is 1. 1 over 8 times 1 is going to be 1 over 8. And that's part A. For part BI, what we're asked to do is use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. Now, we've already sort of explored small angle approximations within this paper already, but sine 2y, when y is small and measured in radians, is going to approximate to 2y. Okay? Therefore, using a small angle approximation, if we know that x is 4 sine 2y, we can approximate that x is going to equal 4 times 2y. Okay, remembering that sine 2y can approximate to 2y when y is small and measured in radians, or when 2y is small and measured in radians. Okay, and what we get is x equals 8y. And if you wanted to take this to the side, get y on the left-hand side of the equation, you can get that y equals 1/8 x. So we almost get a straight line with gradient 1/8. And for part BII, what we're asked to do is explain the relationship between the answers to part A and part BI. Okay, so we're asked to explain the relationship between y equals 1/8 of x and the fact that at the origin, the value of the gradient is 1/8. And what we can see here is that the value of the gradient at the origin is the same as the value of the gradient in this equation that we've worked out here using small angle approximations. So it really is a case of the gradient of BI is the same as the value of dy over dx at the origin obtained in part A. Okay, so without much further ado, let's move on to part C. Part C, okay, show that for all points x, y lying on C, dy over dx is equal to 1 over a times by root b minus x squared, where a and b are constants to be found. Okay, so in essence what it's asking us to do is to rearrange what the value of the dy over dx we had previously, which was 1 over 8 cos 2y, in such a way now where we've got dy over dx being 1 over a times by root b minus x squared, where a and b are constants. Now there are a sort of variety of different sort of trigonometric identities we can use, and the question is a free marker, so I wouldn't spend too much time playing with trig identities, particularly if you may have questions sort of earlier in the paper that you may have left out. But really this is one where you should be looking at this square root and x squared here and thinking of one fundamental trigonometric identity, incidentally the first one that you'll probably learn on A level or in A level maths, and that's that sine squared 2y, and we're using 2y in this case, plus cos squared 2y is going to equal 1. Okay, and in this particular circumstance what we can do is we can move this to the other side, so that cos squared 2y is going to equal 1 minus sine squared 2y, and therefore the cos 2y we've got here is going to equal square root of 1 minus sine squared 2y. Okay, and it's going to equal, so it's going to equal the square root of 1 minus sine squared 2y. So what we can see here now is that we can almost compare this sine squared 2y to the x term that we had before, which was x equals 4 sine 2y. Okay, and what we can see is that if we were to do x over 4, okay, and that equaling sine 2y, if we were to square this, okay, what we'd get here is x squared over 16 equaling sine squared 2y, okay, because we'd have to square the other side too. So this here, okay, is like saying root 1 minus x squared over 16. Yeah. And now what we really want to be doing is we want to be getting rid of this 1 over 16 that's being multiplied by x squared here, so that we've got it in this form here where there is no coefficient to the x squared other than minus 1. And to do that, what I think is handy is if we put this into brackets. So what we'd get is we'd get this here being 1 minus 1 over 16 x squared to the power of a half. And if I was to pull out the half term in a very similar way, in a very sort of similar fashion to the way in which you'd pull out a constant if you were binomially expanding from negative or fractional indices, if I was to pull out 1 over 16 and multiply this by 16 minus x squared, and doing this all to a half, what I'd get is, okay, because what I need to do now is do the work out the square root of both of these terms, I'd get the square root of 1 over 16, which is a quarter, being multiplied by the square root of 16 minus x squared, and this is equal to cos 2y. Okay, and now using the fact that dy over dx is equal to 1 over 8 cos 2y, we now know that it's also going to equal 1 over 8 times a quarter, so 8 over 4. And we're not going to be using cos 2y here, we're going to be using the square root of 16 minus x squared that we worked out previously, and this here is equal to 1 over 2 root 16 minus x squared. Okay, and that there is in such a form where we have dy over dx equaling 1 over a constant being multiplied by the square root of another constant minus x squared. And that there is the answer to question number 14, and that brings us to the end of the paper. And that there was the June 2019 Edexcel Maths Paper 1. It certainly was a good paper. It did cover a lot of the curriculum, a lot of the specification, and I thought that it was quite a provoking yet rewarding paper. So all in all, that was quite positive. But I hope that you guys found this video enjoyable and helpful, and please do like, comment and subscribe and sort of engage with the channel for more content like this. But until next time, thank you very much for tuning in.